kids, Mrs. Geiger here. So, we've been talking about the atom and about atomic theory, as well as we've been looking at how protons and neutrons make up the mass of the atom. Today, we're going to talk about a little bit of math and how we get average atomic masses. So, if you don't have your calculator handy, pause the video and go and grab it. All right, my calculator is right here. I'm going to need it in just a second. So we're going to do a few definitions first. The first thing we're going to talk about is this concept of mass number and how it is different from average atomic mass. So mass number is the mass, it's the mass of each isotope. This is the sum of the protons and the neutrons. All right, so when you add the number of protons and the number of neutrons, and just like the name sounds, the mass number will always be a whole number. All right, because it is that addition of the protons plus the neutrons. Now, how is that different from average atomic mass? And I have average atomic mass here. I have atomic mass in blue because when we abbreviate average atomic mass, we just say atomic mass. So the mass number and the atomic mass are two different things. The average atomic mass is the weighted average of all naturally occurring isotopes. So why do we say naturally occurring? We as humans figured out what atoms are made out of, so then started making our own using a particle accelerator in order to do that. But when we talk about the average atomic mass, we are just talking about the atoms that were created, naturally occurring isotopes were the ones created during the Big Bang. So the ones that are just naturally here in our universe, all right? So it's the weighted average. So what do we mean by weighted average? So atomic masses are the weighted average of the naturally occurring isotopes. You don't need to write that again if you already have that down. Weighted averages use both the mass and the relative abundance of each of the naturally occurring isotopes of each element. So what that means is that it's not a regular average where you add them all up and divide by the number you have, but instead it is a weighted average. So we're going to take into account the relative abundance for each of these isotopes. And relative abundance is always going to be a percentage. So it's the percent of the total, right? So let's say that we wanted to figure out the average age of our class, all right? Now, let's say that I surveyed the class and kids are either, I'm going to make a little T table here. Kids are either 14, 15, or 16 years old. Now, the reason that I'm using age as an analogy here is because when you tell somebody how old you are, you don't say 15.4. I mean, I suppose you could, but let's just use this as an example where just like the mass number, mass numbers are always going to be whole numbers. We're going to use this as an analogy. All right, so think about what data we would need to figure out. What information would we need to use in order to figure out what the average age of our class was? All right, great. So now that you've thought about this, we need to know the number of kids that have each of these ages. All right, great. So let's say that we have 3 kids in our class that are 14. We have 12 kids in our class that are 15. And we have 5 kids in our class that are 16. All right. So we could add them up by saying 14 plus 14 plus 14 plus 15 plus 15 plus 15 plus 15 plus 15 plus 15 plus 15. Was that 12 times? Or we could think about this differently mathematically. When we have relative abundance, so abundance means how much you have. If something is abundant, it has a lot. If something is scarce, it has a small amount. Very often this happens where the term and the positive version of that term have kind of the same idea behind them, the same term. So if we have 3 plus 12 plus 15, that means that we have 20 kids in the class, right? Relative abundance is always going to be a percentage. So right now, figure out what percentage of our class are 14, what percentage of our class are 15, and what percentage of our class are 16 years old. Go ahead and pause the video while you do that work. All right, and so we're back. So you should have gotten 15%, 60%, and 25%. All right, so now how can we figure out the weighted average of the age of our class? So what we're going to do is we're going to take the age times the abundance and multiply them together and then add it to the next. So then we'll have age times abundance plus age times abundance. And since this is a percent, that means that this whole thing is out of 100. So then at the end, we're going to divide by 100. Now in this analogy, we're using age, but in our next example, we're going to use mass. But the idea is the same because it's a weighted average. And this is really just a math lesson on how to do a weighted average. So our first age is 14. And we're going to see up here that that's 15% plus our next age, which is 15. And that's going to be times 60%, right? I'm going to just go back and check. And then we're going to have plus 16 times our abundance, which is 25%. All out of 100. Now let's think about this. Our average of 14, 15, and 16-year-olds should give us a value within the range. So our average must come out somewhere between 14 and 16. And which value is it going to be closest to? 14, 15, or 16? So go ahead and solve for the average. All right, so here is my setup, and I get 15.1 years as my average age of our class. And that makes sense because which age is the most abundant? 15 is the most abundant. So the average should always be closest to whichever value you have the greatest abundance of. All right, so let's do a chemistry example. naturally occurring boron exists in two naturally occurring isotopes. Boron 10 makes up 20%, while boron 11 makes up the remaining 80%. Determine the atomic mass. You might notice I like this one. It's a really simple one. So we're going to do the mass times the abundance plus the mass times the abundance. It's only two isotopes here, so I'm just going to leave it like that, divided by 100. Always very important at the end. So go ahead and plug in. All right, so your setup should look like this. And then you're going to solve for the average here. So our average comes out to 10.8. And the unit here is going to be atomic mass units. We have two isotopes. We have boron 10 and we have boron 11. All right. Now remember, there's different ways that we can write that isotopic notation. I could have written boron 10 and boron 11 like this, or I can write it this way where we put the dash and the value. Now, when you look up on the periodic table, you'll see that it says 10.81. That's because I rounded the percentages to make this question a little bit easier. But let's do a little reality check. 10.8 is closer to 10 or closer to 11? You're right, closer to 11, exactly. So we have an average that's closer to 11 because the abundance of boron 11 is greater than the abundance of boron 10. All right, let's do another example. All right, so here's a Regents question. And this is a question with three isotopes of neon. All right. When you have a question like this, I know that I said that the atomic mass, the mass number is always going to be a whole number. But here we have the atomic mass of each isotope. Because the mass of a proton and the mass of a neutron are based on a carbon-12 standard. They're based on a standard. We didn't have the ability to exactly measure the mass of a proton. Sometimes you get these little decimal points. So when we have this in a question, you're going to always, 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 always use these values that are in the table for your mass. And there we have our natural abundance. So the first question is, in terms of atomic particles, state one difference between these three isotopes of neon. So go ahead and answer that question. All right, great. So you should have said that in terms of, notice it says atomic particles. That means we need to say something about protons and or neutrons or electrons. So in terms of atomic particles, state one difference between the isotopes is different neutrons. They have the same number of protons, and they have the same number of electrons too, but that's not what the question is asking. All right, based on the atomic masses and the naturally occurring abundance shown in the data table, in the space provided in your answer booklet, show a correct numerical setup for calculating the average atomic mass of neon, and then based on natural abundance, the average mass of neon is closest to which whole number. All right, so actually we're going to do a prediction first, and we're going to answer this question first. Based on the natural abundances, the average atomic mass of neon is closest to which whole number? So which of these has the greatest abundance? You got it. It's going to be neon 20, and we're going to make sure that we read the question. It wants a whole number, so the answer to this one is going to be 20. All right, now let's go back and do this question. This based on the atomic mass, the naturally occurring abundances, show the setup. So we're going to have our first isotope, and we're going to have a mass of 19.99. we're going to multiply that times the relative abundance. And then we're going to add them all together. We're going to keep going. 20.99 times the relative abundance is 0.3% plus our last isotope is 21.99 for the mass and 8.8 for the percent. And then at the end, all divided by 100. So go ahead and solve that out while you have it all set up. This is all you would need for the correct numerical setup. So that would get you the point on the regions. But let's solve it for fun. So when I solve this all up, I get 20.17. Now, go back to the reference tables and check. Is that the mass of neon on the periodic table of the elements? It says 20.18, pretty close. That's just because of a rounding difference, mostly in this mass of the isotope 21. But it's really, really close, and that's just because of rounding differences. All right, so when you solve this, even if you just need the correct numerical setup, I like to always solve it, and then I can check my answer because the average is on the periodic table. So you're never going to be asked just for the average because that's on the periodic table. Instead, you're going to be asked, what's the setup? All right, one more practice problem. 98.93% of the carbon atoms have a mass of 12.00 atomic mass units. 1.07% of the carbon atoms have a mass of 13.00 atomic mass units. The space provided in your answer book will show the correct numerical setup for calculating the average mass of carbon. So go ahead, pause the video, and solve for that. All right, so I have the mass times the abundance, so 12.00 times 98.93, plus the mass times the abundance, 13.01 times 1.07, all divided by 100, and I end up with 12.01 atomic mass units, which is exactly what it says on the reference tables. Now, there's another way to do this where instead of dividing by 100 at the end, you change the percentage into the decimal percents. There's a reason I don't do that. And the reason I don't do that is because when I change these numbers into decimal percents, I could write this equation out differently. I could write it like this. 12.00 times 0.9893, so that's the decimal percent there, plus 13.00 times 0.0107. Now that's the same exact setup. I'm dividing both of these by 100. But the reason I don't like to do that this way is because when there's a small percentage like this, here 1.07%, very often kids make the mistake of putting in 0.107 and they lose that extra zero. And instead of putting in 1%, they put in 10%. Or like in this question, where we have this here, this 0.03%, the decimal percent for 0.03 is 0.003. And kids very often make that mistake. So I usually like to just do it this way. Keep the numbers the same, just divide by 100 at the end, and you'll always get the right answer there. All right. Oh, describe in terms of subatomic particles found in the nucleus one difference between the nuclei of carbon-12 and the nuclei of carbon-13. Your response must include both isotopes. So, in your answer, you need to have carbon-12 and carbon-13 and it needs to be in terms of subatomic particles found in the nucleus. So you can say that carbon 12 and carbon 13 have a different number of neutrons, or you can be very specific, and you can say that carbon 12 contains 6 neutrons, while carbon 13 contains 7 neutrons. All right, you can say that carbon 12 has fewer neutrons than carbon 13, or that they have a different number, or you can be very specific. All of those would be correct answers.